Hello, welcome to the section on multi-class classification. So remember the key ideas here. We're trying to do classification where the target variable can take one of k possible values. And we have raw target values, which are, say, numbered 1 through capital K. But we embed those using the map y is equal to psi of v, and as a result y can take one of capital K values psi 1 through psi capital K. Each one of those is a vector in Rm. We get to choose what m is, we get to choose what those psi 1 through psi k's are. And once we've got a predictor that produces a y from an x, we have to get back to a v, and the way we do that is we look at the y hat that we've got produced by the predictor, and we look over all of the different psi's, psi 1 through psi k, to find the one that's closest to the y hat. And that's going to tell us which of the classes to unembed and give us the resulting v hat. And of course the predictor that produces y hat from x is constructed via regularized empirical risk minimization. Now at the end of the day, what we do is we validate using the Neyman-Pearson performance metric on the test data. So we've picked our kappas, where kappa j is our distaste, our displeasure in mistaking bj, and our performance metric is then the sum over j of kappa j ej, where ej counts the number of times that we mistook vj. And of course, if all the kappas are 1, that's just the error rate. Now we're going to want to construct a loss function. And it's not quite so easy as it was in the Boolean case. So in the Boolean case, remember how it worked. Let me just use this as a little sketch pad here. We embedded, so this is Rm, where m is 1. So we embedded at +1 and -1. We'll call this psi 1 and psi 2. And then we had ideal loss functions from the Neyman-Pearson loss. So if the true y was 1, then our ideal loss function would be this. Our ideal loss function would be this, and it would say that since y was 1, our ideal y hat should be anything negative. So we want to generalize this idea to the case where we've now got multiple psi i's, not just 2, and we've embedded them in Rm, and m is not just 1. So the first idea we need is simply to know when a vector is closer to one point than another point. And that's, so here we have 2 points. We have point A and point B. And we have here this green line, and this green line is the perpendicular bisector of those 2 points. And that comes about mathematically in the following way. If I ask when is a vector y hat closer to A than it is to B, well, the distance from y hat to A is just the norm of y hat minus A, and the distance from y to B is the norm of y hat minus B. And so we can ask ourselves the question, when is one closer than less than the other? That's this inequality right here. Now we square both sides, those are both 2 norms. What happens is we get an expression which looks like y hat minus a norm squared is less than or equal to the norm of y hat minus b squared. And if we expand those squares, well, then we get that the y hat transpose y hat minus 2a transpose y hat plus a transpose a is less than or equal to y hat transpose y hat minus 2b transpose y hat plus b transpose b. And the nice thing about this is that those quadratic terms in y hat go away, and this inequality reduces to this inequality. It is this inequality. 2b minus a transpose y hat minus the norm of b squared plus the norm of a squared is less than 0. And in particular, the thing to notice here is that this only depends on y hat in this nice simple way here. Right? It's a vector transpose times y hat. And so this is equal to 0 along this green line. It's less than 0 when y hat is on the a side, and it's greater than 0 when y hat's on the b side of the green line. And the decision boundary, explicitly just replacing that inequality with an equality, is right here. That's a hyperplane. That's an equation of the form C transpose y is equal to D, where C is a vector in Rm and D is a scalar. And here in particular, C is 2b minus a, and D is the norm of a squared minus the norm of b squared. And this hyperplane has to pass through the midpoint of a and b. And you can check that it does by substituting y hat is a plus b on 2 into this equation right here and checking that you get 0. Now, we can use this analysis to construct a notion of signed distance from the hyperplane H. So the hyperplane H is here. It's this green hyperplane that's the perpendicular bisector between A and B. And we're going to say that we're going to measure the distance from H. And so I'm going to have some points on this side and some points on this side. And these points we're going to say are distance minus 1 from the hyperplane H. And these points we'll say are distance 1. So instead of labeling them both as having distance 1, the ones on one side will get negative distance and the ones on the other will get positive distance. And our point y hat here has some distance here which is about minus 2 from the hyperplane. I might have another point, say over here, and that would have a distance plus 2, or maybe slightly more than 2, the way I've drawn it from the hyperplane. And where does this formula come from? Well, we have this nice formula here, which is this inequality here, which is defines for us which side of the hyperplane we're on. And it has the form of C transpose y plus D. Now, over here, we've simply taken that and taken that the value of the left-hand side of that inequality and made it equal to our distance measure. But we've scaled it. We've scaled it by 2 the norm of b minus a. And as a result, d has this form. D is equal to u transpose y plus v, where u here is a unit vector. It's b minus a divided by the norm of b minus a. And because u is a unit vector, it's measuring distance, which is corresponding to the unit distances that we use in the plane. So in other words, if y hat actually is a distance d from the hyperplane, then capital D here will be the appropriate sign appended on to y hat. So D is 0. That's the decision boundary. That's the decision boundary that decides whether we're on the A side or the B side of the hyperplane. And if it's negative, we're closer to A than we are to B. So why do we want a notion of signed distance? And the idea goes like this. Suppose we have, let me draw a picture. So this will be R2. So here M is 2. So we've embedded our categorical variables in the plane R2. And the embedding points, well, let's just pick them. Let's put 1 over here, 1 over here, and 1 over here. And I will label those psi 1, psi 2, and psi 3. And those are the points to which our categorical target variables embed. Now, with those points, we're going to say, okay, well, those are our embedded points. We'd like to define a loss function with those points. That's what we'd like to do. Now, the idea is, of course, is that we're going to have a predictor that produces for us a y hat. And we would like that predictor to be inclined to give us a y hat that's close to psi 1 when y is 1, and a y hat that's close to psi 2 when y is 2, and a y hat that's close to psi 3 when y is 3. So let's divide up the plane into regions, the Voronoi partition of the plane, like that. And then this region right here is the region which, if we have a y hat within that region, then it's unembedded back to psi 1, and therefore back to the target value corresponding to psi 1. And so what we'd like is we'd like to have a loss function which encourages y hat to lie within that region when y is equal to psi 1. We can imagine such a loss function. Here's what it would be. It would be 0 if y hat lies in that region, and 1 elsewhere. It would be 1 here, and 0 here. And such a loss function would count up for us the rate at which we mistook y1 for something else. And so in our loss function, if we summed up that and divided by n, that would give us precisely the rate which we mistook for y1 for something else. And so kappa 1 multiplied by that loss function would count up for us the Neyman-Pearson contribution of the loss for the target psi1. And then we would do another one. We'd have a loss function. Of course, we've got a different loss function for y1, y2, and y3. And so if this is y1, this is y2, this is y3, I would have a loss function which was 0 here and 1 here, and that would be the loss function corresponding to y is equal to 2. And so we have 3 different loss functions, functions of y hat, one when y is psi1, one when y is psi2, and one is when y is psi3, and each one is 0 on the region corresponding to its psi I. So how do we construct such a loss? Well, what we can do is we can use the signed distance functions, dij. And what dij is going to be, it's going to be the distance, the signed distance of y hat from the boundary between psi I and psi j. Let's look back at our example. This is psi1, psi2, and psi3. Now, d1, 2 is less than 0 when we are closer to psi1 than we are to psi2. So d1, 2 is less than 0. Where is that? That's everywhere to the left of this line. Where is d1, 3 less than 0? That's everywhere below that line. Let me mark my 2 lines. And so if d1, 2 and d1, 3 are less than 0, well then I'm in the region belonging to psi1. And similarly, I'm in the region belonging to psi2. That's this region. If d2, 1 is less than 0 and d2, 3 is less than 0, and finally over here I have d3, 1 is less than 0 and d3, 2 is less than 0. So in other words, I need, for any given region, for any given I, if I want y hat to be in the region belonging to psi I, then I need dij to be less than 0 for all the other j's. Now that we've got these signed distance functions, we can use them to construct our ideal loss functions. Here's some examples to be explicit in the most common cases. The most common cases are, of course, the Boolean. In the Boolean case, m is 1, and so I've just got r here. Psi1 is minus 1, and psi2 is 1. And then I've got d1, 2 is less than 0 over here, and d2, 1 is less than 0 over here. And so if y is in the region corresponding to psi1, so that means that y is minus 1, well then we would like d1, 2 to be less than 0, and that would be, and then we'd have a loss function which was 0 over here, say, and large over here, and that would be our ideal loss function, our Neyman-Pearson loss function. Similarly, if y is plus 1, then we want d to 1. If y is plus 1, then that corresponds to psi 2, and so we want d to 1 of y hat to be less than 0, and d to 1 of y hat is minus y hat, and so we want y hat to be greater than 0. If we look at the one hot case, that's their psi j, this should say ej, let me just correct that, psi j is ej, if we compute what dij is, well, the distance between dij, let's just look at it. This is psi 1 and this is psi 2 in 2 dimensions if we're embedding using one hot. This is, of course, 1, 0, and this is 0, 1. And so the distance between those 2 points is simply root 2. And so dij is yj minus yi on root 2, where in order to compute that, of course, we've used our definition here. 2b minus a transposed y hat divided by 2 the norm of b minus a. Obviously the 2's cancel, and b minus a transposed times y hat gives us y hat I minus y hat j, or y hat j minus y hat I, depending on the sign. So when y is ei, we want the max over all j not equal to I of dij to be less than 0. And that means that we want y j minus yi to be less than 0. And that's the same as saying that yj is less than yi. So in other words, we would like the corresponding component of y hat to be the maximum component of y hat. So let's use these to construct loss functions explicitly. What have we got to do? Well, we've got to give k different loss functions, one corresponding to each of the possible values of y. Remember, loss is a function of y hat and y here can only take k possible values, which we've denoted as L of y hat comma psi I. It's how much we dislike predicting y hat when y is psi I. In other words, if, to come back to our example, if d12 is less than 0 and d13 is less than 0, then we'd like the loss function corresponding to L of y hat psi 1 to be small and large when y hat doesn't satisfy these two conditions. And that gives us immediately the Neyman Pearson loss. We can set a loss function of 0 on the region corresponding to psi I and kappa I elsewhere. And that means when we take the average of that Neyman Pearson loss, we get kappa I times the frequency with which y hat is mistaken. Y hat gives an answer which is not I when y truly is I. And this is, of course, the analog of our nice square loss functions that we've seen before. Now the downside is, of course, that it's hard to minimize these discontinuous loss functions which have derivative 0 almost everywhere. And so instead we use what's called a proxy loss, a loss that approximates the Neyman Pearson loss but is more easily optimized. So we either would like it to be convex or differentiable or both. So here's perhaps one of there are two really common loss functions that are used. One is the hinge loss. This is the multi-class hinge loss. It's kappa I times the maximum of 1 plus dij of y hat, and we're maximizing it over all j not equal to I. And this is a loss function which is 0 if y hat is in the right region with a margin of at least 1. And so it has to be not only within the right region, but it has to be deep within the right region. And this is a convex but not differentiable loss. If you use quadratic regularization, then it's a multi-class support vector machine. If we have a Boolean embedding, then psi1 is -1 and psi2 is 1, then it reduces to the usual hinge loss that we've seen before. It's 1 plus y hat, the positive part, times kappa 1, when y is -1. And it's the flip of that when y is 1. Here is the corresponding surface plots for it in the case which we've been discussing so far. This is our example. We've got 3 psis, psi1, psi2, and psi3. And you can see you've got a loss function which is convex, which is piecewise linear, and which is 0 when you're deep within each of the 3 regions. So of course we've got 3 loss functions here. In the top right graph here, we have the loss function corresponding to the case when y is 1, y is psi1. In the bottom right, we have the case where y is psi3, and in the bottom left, we have the case when y is psi2. Now, if you look in particular at the top right, when y is psi1, you can see that the loss function is 0 when we are deep within the region corresponding to y1. Here's the other most common loss function, the multiclass logistic loss. So this is the following. This is the log of the sum of the dij's. So if all of the dij's are less than 0, then this is going to be, well, the sum of e to the negative numbers, and so it'll be a relatively small quantity, and it will grow as the dij's grow. It's convex and differentiable. It's called a multiclass logistic loss, and if we use this as our loss function, we're doing multiclass logistic regression. So here's a plot of that loss function. Again, we can see 3 different loss functions, each one associated with a different region of the plane corresponding to our different representatives. And for each one, the loss function is small on the corresponding region and grows outside the region. The Log-sum-exp function is what's at the heart of this loss function. This is an interesting function because it is convex differentiable and it's approximately the maximum function. Sometimes people call it the softmax function, but you should be careful about that because there are other functions also used in machine learning, as it happens, that are also called the softmax function. One of the nice things about the Log-sum-exp function is that we know how far it is from the max function. It's always greater than or equal to the maximum of the xi's, and it's always less than or equal to the maximum of the xi's plus log n. Let's look at an example. This is a 3-class example. This goes back to 1936. It's a very famous data set which was collected by the statistician Fisher. He took measurements of 150 different plants, all of which were 3 different species of iris. So there's 50 from each of the 3 different species. And for each of those samples, he made 4 measurements: the sepal length, the sepal width, the petal length, and the petal width. We can plot them here. So this is simply an arrangement of all the data. So for example, in this plot on the top right, we've plotted sepal length on the vertical axis against petal width on the horizontal axis. You can see that there are 3 species. The reds, one of the species is indicated in red, one of them in green, and one of them in blue. You can see that telling the red from the others is rather straightforward, and telling the green and blue apart is a bit more difficult. So here we've done classification with using only 2 of the features, sepal length and sepal width, and those are plotted in this figure. Again, we can see green dots, blue dots, and red dots, and it's relatively easy to separate the red dots. And this is using a linear predictor with one-hot embedding, multiclass logistic loss, and we're minimizing the probability of error so that the kappas are all 1. And here, there's no training and test set. We've simply trained it on all the data. Of course, if we had more data, we would be using a training and test set, and would also be using regularization. The confusion matrix shows us what we can see from the figure, that we've got all the red dots perfectly correct. We haven't mistaken anything for a red dot, but some of the greens and blues we've got wrong. We've mistaken 12 greens for blues and 13 blues for greens, and as you can see in the figure, there's no clear way to separate the greens from the blues. Now, if you do classification with all 4 features, of course we can't plot it anymore. Same thing, one-hot embedding, minimize the probability of error. Well, then you can do much better. Then you can get a confusion matrix where there's only 1 error out of our 150 plants. 2 errors, 2 misclassifications. We've got 1 blue classified as green and 1 green classified as blue. So let's summarize. When we're doing multi-class classification, we'd like a loss function that encourages the correct unembedding. So when y hat is close to psi I, well then we want L of y hat psi I to be small, and we want it to be not small when y hat is not close to psi I. The most common losses people use are the multiclass hinge loss and the multiclass logistic loss. And these 2 classifiers are called the SVM and the logistic classifiers. And both of these losses are convex, so we can solve easily the ERM or the REM problems in the case where the predictor is a linear predictor.